Every year, without fail, something happens in Saudi Arabia that has no comparison anywhere else on earth. 2 million people, not spread across a country, not distributed across a week, but gathered in a single city. They move toward a single point, performing the same rituals at the same time. This is Hajj, the annual Islamic pilgrimage to Mecca, and by any measure of human logistics, it is the most demanding crowd event ever attempted. To put that number in perspective, the entire population of Houston, Texas, compressed into an area smaller than many American suburbs. Every person arriving within days of each other. Every person needing to eat, sleep, stay cool in temperatures that routinely climb above 110 degrees Fahrenheit, and then move, together, through a sequence of religious obligations that follow a strict geographic and time-based order. There is no flexibility in the schedule. The rituals of Hajj are tied to specific days on the Islamic calendar. You cannot delay them. You cannot spread them out. 2 million people must be in the right place at the right time every single year. For most of history, this was managed through sheer faith and human endurance. Pilgrims arrived on foot, on camels, by ship. The city of Mecca absorbed them as best it could, and for centuries that was enough, because the numbers, while large, were manageable. But the 20th century changed everything. Air travel made Mecca accessible to Muslims from Indonesia, Nigeria, the United States, Bangladesh, and 100 other countries. Participation exploded, and the infrastructure of a medieval holy city was suddenly being asked to handle something it was never designed for. The consequences were deadly. In 1990, a tunnel stampede killed over 1,400 people. In 2006, more than 300 pilgrims died in a bridge collapse triggered by crowd pressure. In 2015, a stampede near the Jamarat Bridge, where pilgrims performed the ritual stoning of the devil, killed over 2,400 people in what became one of the deadliest crowd disasters in recorded history. Each tragedy carried the same brutal lesson. Faith alone cannot move 2 million people safely. Engineering has to do it. That realization forced Saudi Arabia to ask a question that no government had ever faced at this scale. How do you design a system, underground, above ground, and everywhere in between, that turns the most chaotic human gathering on Earth into something that can be survived, managed, and repeated year after year? The answer begins beneath the surface, in a network of tunnels that most of the world has never heard of. For decades, the Saudi government treated Mecca's crowd problem the way most governments treat infrastructure problems, reactively. A disaster would happen, an investigation would follow, a report would be filed, and some targeted improvement would be made. Widen a road here. Add a barrier there. Install more water stations along the pilgrimage route. The underlying assumption was that the system was basically sound and just needed patches. That assumption died on July 2, 1990. A pedestrian tunnel connecting the Grand Mosque to the tent city of Mina became a killing ground. Ventilation failed. The air inside turned into a furnace. Pilgrims began pushing toward the exits. The crowd compressed. People fell. And in the chaos of 1,426 human beings trapped in a concrete tube with nowhere to go, the tunnel became a trap. It was the deadliest single event in the history of Hajj in the modern era, and it happened not because of bad intentions, not because of negligence in the traditional sense, but because the infrastructure had been designed for a different scale of human movement than what actually showed up. The investigations that followed revealed something uncomfortable. The problem was not just that one tunnel. The problem was that every major choke point in Mecca, every bridge, every pedestrian corridor, every plaza surrounding the Grand Mosque, was operating beyond its safe capacity during peak pilgrimage hours. The city had been expanded repeatedly, but always in response to growth that had already happened, never in anticipation of growth that was coming. Saudi Arabia was perpetually building for the crowd of 5 years ago. After the 2006 bridge collapse, the calculus changed. The Saudi government launched what would become one of the most expensive and complex urban redesign projects in the history of religious infrastructure. The Jamarat Bridge, The site of the stoning ritual, where crowd pressure had repeatedly proven fatal, was completely demolished and rebuilt as a 5-level structure capable of processing 300,000 pilgrims per hour. That single redesign required computer modeling of crowd fluid dynamics, a discipline borrowed from the physics of liquids and applied to human movement at mass scale. But the bridge was only the beginning. Engineers studying the full map of Mecca's pilgrimage routes recognized that surface-level solutions had a hard ceiling. Streets can only be so wide. Plazas can only hold so many people. As long as 2 million pilgrims were competing for the same ground-level space, the math would never fully work. The only way to genuinely separate and control flows of that magnitude was to stop thinking horizontally and start thinking vertically. The crowd had to go underground. What exists beneath Mecca today is not a single tunnel. It is a layered underground system that took decades to build, costs billions of dollars to maintain, and functions less like a subway and more like a circulatory system. This system is designed not just to move people from point A to point B, but to regulate pressure, prevent blockages, and keep the entire body of 2 million pilgrims alive and flowing. The most critical artery in this system is the Mina Tunnel Complex, running beneath the Valley of Mina, the tent city where pilgrims spend 3 days during the peak of Hajj. The tunnels stretch for nearly a mile and connect key ritual sites that every pilgrim must visit in sequence. Before they existed, that valley became a bottleneck of historic proportions every single year. Hundreds of thousands of people moved in opposite directions along the same surface roads, in midday heat that turns asphalt soft and pushes body temperatures toward dangerous thresholds. The engineering solution had to solve multiple problems simultaneously. First, separation. Pilgrims moving toward the Jamarat for the stoning ritual cannot share space with pilgrims moving away from it. When they do, crowd pressure builds at the collision points and people die. The tunnels allow directional flow to be split across different levels and different corridors so the two streams never meet. Second, temperature. Saudi Arabia, in the month of Hajj, is not simply hot, it is physiologically threatening. Tunnels that trap heat become ovens. The Mina complex is equipped with a mechanical ventilation system that pushes cooled air through the passages continuously, keeping internal temperatures low enough that the underground route is actually safer than the surface in terms of heat exposure. Third, capacity. The tunnel cross-sections were engineered to specific width and height ratios calculated from crowd flow modeling, the same discipline that redesigned the Jamarat Bridge. This ensures that even at maximum occupancy, movement remains possible and pressure does not build to crushing levels. The materials used throughout the system reflect the unique demands of the environment. Concrete formulations were selected for thermal performance in extreme heat. Wall surfaces are finished to minimize friction and injury if contact occurs. Lighting systems are redundant because a power failure in a dark tunnel filled with hundreds of thousands of people would be catastrophic. Emergency exits are spaced at intervals determined by evacuation modeling, not by construction convenience. Above all, the system was designed around a principle that sounds simple but is extraordinarily difficult to execute at this scale. Never let the crowd stop moving. A stationary crowd is a dangerous crowd. The tunnels are not holding areas, they are channels, and everything about their geometry, airflow, lighting, and exit placement exists to keep 2 million people in motion. Building the tunnels was the hard part. Running them is harder. On any given peak day of a Hajj, the operations center overseeing pilgrimage movement looks less like a city government office and more like a military command room. Screens cover entire walls. Feeds from thousands of cameras stream in real time from tunnel entrances, corridor junctions, plaza approaches, and the ritual sites themselves. A team of analysts watches crowd density maps that update by the minute. Color-coded overlays showing where foot traffic is light, where it is building, and where it is approaching the threshold that precedes a dangerous compression event. The fundamental challenge of managing 2 million people through a tunnel system is that the tunnels themselves create a timing problem. You cannot simply open the gates and let everyone in at once. A tunnel has a fixed capacity. If pilgrims enter faster than they exit, pressure builds from behind. The people at the front slow down. The people in the middle have nowhere to go. The people at the back keep pushing forward because they cannot see what is happening ahead of them. This is exactly the chain of events that has produced every major pilgrimage disaster on record. The operations center exists to break that chain before it starts. The primary tool is wave scheduling. Pilgrims are divided into groups by nationality, by camp location, by registration number, and each group is assigned a specific departure window for each ritual. The stoning at the Jamarat happens across 3 days, and the schedule staggers the 2 million participants across those days and across the hours within each day with the precision of an air traffic control system. No group moves until the previous wave has cleared the tunnel and dispersed at the destination. The timing is calculated using flow rate data from the tunnels themselves, sensors embedded in the floor, and walls measure pedestrian density and walking speed continuously, feeding live numbers back to the operations center. When density in a corridor crosses a warning threshold, the response is immediate. Entry points upstream are slowed or temporarily closed. Crowd management teams deployed throughout the tunnel network redirect foot traffic toward alternative routes. Announcements in multiple languages guide pilgrims away from congestion points. In some sections, one-way flow protocols are activated automatically. Gates and barriers controlled remotely from the operations center physically prevent movement in the wrong direction. The entire system depends on one thing that no amount of engineering can fully guarantee: that 2 million people, many of whom have traveled from the other side of the world to perform one of the most emotionally significant acts of their lives, will follow instructions from a loudspeaker in a concrete tunnel. The fact that it works, not perfectly, but well enough to move this many people this safely, year after year, is its own kind of miracle. Beneath the operations center, beneath the crowd flow models and the density sensors and the wave scheduling, there is another layer of infrastructure that most pilgrims never see, and, if everything goes right, never need. It is the emergency system, and in a tunnel network moving 2 million people through extreme heat, it has to be ready for everything at once. Heat is the first enemy. Mecca, during Hajj, sits at the intersection of two crises: outdoor temperatures that regularly exceed 110 degrees Fahrenheit, and a population that includes elderly pilgrims, pilgrims with chronic conditions, and people who have traveled from cooler climates. Their bodies have not adapted to the Arabian Peninsula in summer. Heat stroke can develop in minutes. A pilgrim who collapses in a tunnel corridor does not just become a medical emergency. They become an obstacle in a space where obstacles can trigger the exact chain reaction that operations teams spend every waking hour trying to prevent. Speed of response is not a courtesy. It is a structural requirement. Medical stations are positioned throughout the tunnel network at intervals determined by response time modeling. The target is that no point in the system is more than a few minutes from trained personnel. Each station is equipped for heat emergencies specifically: cooling equipment, intravenous fluids, oxygen, and direct communication lines to the surface hospitals that Saudi Arabia deploys in extraordinary numbers during Hajj. In peak years, the kingdom operates field hospitals with thousands of beds within the pilgrimage zone, staffed by medical teams from multiple countries. The tunnel medical posts are the first link in that chain, designed to stabilize and extract before a single collapsed pilgrim becomes a crowd event. Fire is the second concern. The tunnel walls carry electrical conduits, ventilation ducts, lighting systems, and communication cables, all of it running through enclosed concrete passages filled with people. Fire suppression systems are embedded throughout, with automatic triggers that do not wait for a human decision. Smoke extraction protocols activate independently of the ventilation system, reversing airflow to pull combustion gases away from occupied corridors. Emergency lighting operates on independent power supplies so that a main electrical failure does not produce darkness. Evacuation routes are marked, lit, and, critically, kept clear at all times. During peak hours, dedicated personnel stationed at evacuation exits do nothing else but ensure those exits remain accessible. They are not crowd managers in the general sense. Their only job is to make sure the door opens when it needs to. What makes this system remarkable is not any single technology. It is the redundancy, the insistence that every critical function has a backup, and that backup has a backup. In a tunnel under Mecca during Hajj, there is no acceptable single point of failure. When the last pilgrim exits the tunnel system and Mecca begins its slow return to a city of 4 million rather than 6, the engineers and operations teams who ran the system for 5 days do something that might seem premature given how recently everything ended. Start preparing for next year. That cycle, build, operate, debrief, improve, repeat, is what separates Mecca's pilgrimage infrastructure from almost every other crowd management system on Earth. Most cities design for their peak events and then leave those designs largely unchanged for decades. Mecca cannot afford that approach. The pilgrimage grows. The demographics shift. Climate change is making the Arabian Peninsula hotter each decade, which means the thermal engineering assumptions built into the tunnel ventilation systems in the 1990s are being tested against conditions their designers did not anticipate. Every year that passes without a major disaster is not proof that the system is finished. It is proof that the system is working well enough to survive one more iteration, and that next year it will need to be better. There is something in this story that goes beyond engineering. Hajj exists because of a belief held by nearly 2 billion people that this pilgrimage, performed correctly, carries a spiritual weight unlike anything else available to a human being in this life. The people moving through those tunnels are not commuters. They are not tourists. They are people who saved for years, traveled thousands of miles, and arrived carrying the full weight of what this journey means to them and their families. The infrastructure exists to protect that. Every sensor, every medical station, every redundant power supply, every carefully calculated tunnel width is, in the end, an act of respect for what those 2 million people came to do. America builds infrastructure for efficiency, for economic output, for competitive advantage. The infrastructure beneath Mecca was built for something older and harder to quantify: the belief that human life is sacred enough to deserve systems engineered to protect it, even when the scale of protection required is almost incomprehensible. 2 million people, 5 days, 1 city, underground tunnels that most of the world has never seen, managed by systems that most engineers will never work on, protecting a ritual that has continued without interruption for 14 centuries. The tunnels are new, the pilgrimage is ancient, and the fact that one can now serve the other, safely, repeatedly, at this scale, is one of the most quietly extraordinary engineering achievements of the modern world.